Okay, for chapter 6, we are in 6.2 today. And 6.2 basically takes, there's a couple of ways you can do 6.2. They talk about all kinds of different methods on these that we're going to do. But basically, it's keying on a 3x3 system or like a 4x4 or a 3x4 system where it kind of takes a step up on some parts of it. And so we'll just, I guess the best way of saying it's just larger systems of equations. The main thing we're going to do when we go through this part would be on on the 3x3s, but they also kind of mix in some other parts of it to kind of talk about some different things that's there. So I guess probably the biggest thing is that no matter if it's a 3x3 system or a 3x4 system, whatever you're going to do, the biggest thing that a lot of cases you're going to do for these parts is you're going to use back substitution to solve. And basically on that one, it's similar to kind of like what we were doing back in 6.1. It's on a bigger scale. So it may be that you might start with, just to kind of give you an idea of what they're talking about here. Just so you have an idea of what it looks like when we're talking about the back substitution. They may give you a system that may kind of look something like this. And probably more than likely is that we would eventually have a system where maybe this starts with x on all three of these equations, or maybe even all four of these. And eventually you're going to narrow it down so that it has this kind of tapered look to it. So that when you solve it, you get it down so that you've got one variable here, you've got two, and you've got three. So really that's kind of the way that you want things to look on those, is that no matter what you do, if it was a 3x3 system, you would kind of work it down so it looks something like this. So you could solve this part and then feed this one back in. And then if it was a 4x4, you basically kind of do the same thing. It still has those same things we were doing back in section 1 last week, that you can multiply one row by some number to help eliminate some variables. You can do all those things. And even with this one, a lot of times when especially if you've got an equation that you're going through, if you see one of these equations like this one that has it where it's all multiples of 2, or this one has multiples of 3, you can divide all the numbers by 2. So you could even take, this equation, just to save us from rewriting it here, but where this one is all divisible by 2, you could take this equation and divide everything by 2. So really this would just be z plus w equals -3. So whenever you see problems like that, just realize you can do the same thing. But with back substitution is they want you to start where you have just the one variable that's here, and you'll solve for this one variable. And then once you have that one variable, then you're going to, the back substitution part is that you just go back to the next equation and you can plug it back in here to solve for z then. So this one will actually go back and plug it back in here. So that's z plus 3 equals -3. So z would equal -6. Then you can take these two values you have to then plug it back into here. Okay, so we'll plug in the 3 for the w, the -6 for the z. Both those are pluses, or a little bit like that. So that would be y minus 3 equals 4. Add 3 to both sides, so we get y equals 7. And then you would take these three values and plug it back into the original equation that you have on the very top of it back here, which lots of times people call that equation 1. So then we'll take x plus 3y minus 4, 2w equals 1. And again, we're going to take these three values to plug it back in here. So we've got x times 7 minus 4 times negative 6 plus 2 times 3 equals 1. And then just work this problem out from here. So that's x plus 21 plus 24 plus 6 equals 1. So that's 30 plus 20, that's 51. Subtract the 51 from both sides. So then we get x would be negative 50. Okay, and the way, because these problems get bigger, what they're going to do is they're not going to have the variables out of order and out of place like it was in the last section. This one, you pretty much put your answers back in the order that they give the variables here. So this is in X, Y, Z, W order. So when you write out the answer, instead of it being an ordered pair, in this case, it would be like an ordered quadruplet, however how you want to say that. You'll start with your X value. Then you'll go to your Y value, then Z, and then W. And I know that makes no sense because W should have been first, but most of the time they start with X and Y and then Z, and then when they went to a fourth variable, they just throw W at the end. I don't know why they do that, but that's just kind of the way that things set up. So a little odd that they would do it that way. But on all the problems that you'll do, they'll basically be set up in that order. They always start with X and Y, and then they got to Z, and then they were like, oh, there's 3, well, then we need a fourth one. Well, there's nothing after Z, so then they went back to what was in the beginning of it. So the order doesn't make any sense. Just realize that that's the way it'll go on any of these problems that they do. Okay, so when they talk about back sub, and again, we basically did the same thing back in section 1. It was just a 2 by 2 that we would take. If we go back to what we're doing back in section 1, you basically were just taking the 2 equations and you were eliminating either the x's or the y so that you had just one variable and you could solve it, and then you would plug that back into any equation. It's still that same concept, but it's just a bigger set of problems that you're going to have to do when you go through those. Okay, so that's all the back substitution is, just taking one variable, plugging it into the equation above it to find the next variable, and then just keep repeating that pattern as it goes back and forth on all those. Okay, and then they're going to tell you also that you can, and just like we were doing before, you can take, like we did back in section 1, that you could take any equation and you could multiply it. If we were just kind of flashing back here for just a second, you don't have to write this down. It's just going back and kind of remembering what we were doing last time. That you could take if you had a system like this, that you could take the top row here, multiply it by -4, and then you could add these 2 equations together. Okay, so then that would knock that out. You get -17y would equal -38, and then you could solve for y from there, from that part. What they're going to do in this case is they're going to call this, when they start talking about these, is that a lot of times you'll see where it talks about this is equation 1 and this is equation 2. For this part of it, they're not going to call it equation 1, equation 2. They're just going to call it row 1 and row 2. If we go back to this problem that we had back here, they would have called this row 1, row 2, row 3, and then row 4. And they're just going to have you do some operations on these. So like for this problem, this would have been one where they would have said you would do 4 times row 1, or -4 times row 1, and then you're going to add that to row 2. So when they talk about the operations and things, that's what they're going to talk about doing, is that basically you're just taking these two things, putting it together, and then this would be the result you would get. This would be like a new row that you're going to have that you would have from this part. Now, if this had been, like 34, we'd made this a 6. Then we could divide those two things out and got that y would equal 2, something like that. But they're going to tell you that you can do operations on these. They're going to tell you that it's still that same thing we were talking about before, that you can multiply by any non-zero number and you can still add that to another equation, which in this case they're calling them rows instead of equations. So you can do operations that way. So they may show you something like this, that they may tell you to do -4 times row 1 and add that to row 2. Still the same thing we were doing before. They're just kind of putting a new notation when you see some of those options when it comes off of it. Okay, so that's one thing that they'll kind of throw at you, and it's still the same thing we were doing last time. It's just that they're giving it more of a fancy term now, but it's still just kind of doing the same thing. Okay. All right, so then they give you a bunch of options of different things that you can do and different ways to solve. And I'll be honest with you, I'll show you some different parts, so just kind of so when you see some of these, you'll know what it is they're talking about. But to me, there's always really one easy way that you can do this that's pretty much the same thing every time that'll work. It just may not be exactly what they called for it to do. Because sometimes people get caught up on, doing it this way or doing it that way, and really they're all going to work. It's just a different way to kind of get to a problem. Okay, so one of the ways that they show you is they talk about an augmented matrix. And basically, for the augmented matrix, what it does is that for any system that you have, it separates the variables from the constants. By a vertical line. And then also removes the variables. Okay, so it basically would be something like this. Let's say this was a 3x3 system. And when you talk about the 3x3, you're talking about the rows and the variables. So if you've got 3 rows and 3 variables, it's a 3x3. Everything we did last time at 6.1 were basically 2x2s because we had 2 equations and 2 variables. Okay, so this was the system that you started off with. If they ask you to rewrite it in augmented matrix form, basically here's all you do. You just take the numbers that you have that's here and you just write down the numbers. So there'll be 2, 1, 1. And then you draw a vertical line where all the equal signs are, and then you put the 3 that's over here. It's 3, -4, 2, -5, 1, 1, 1, and 2. Okay, and sometimes people go, well, what does that do? Well, some people don't like having the variables in here, and then they would tell you to solve this part and kind of go through and do everything else that you have with it. Some people are like, I don't, it's the same thing. it's still basically doing the same thing. It's just one has variables and one doesn't. So it's just a matter of, for some people, they kind of like having this because they don't have to write down all the variables. And you're still going to do the same thing that we were going to do before. You're still going to try to rewrite these equations so that you've got where you can go back and solve and do some solving parts on these. But I think a lot of the parts of what it's going to ask you to do is it's just going to say, all right, just know that this is, an augmented matrix form, and this is a system that, and you can basically interchange back and forth on these two. How you solve it, it's still basically the same way. Okay. One of the other ways that they will give to you and talk about is reduced row echelon form. And with the reduced row echelon form, it basically takes this augmented matrix that you have, and basically is this. It has ones on the diagonal on the left-hand side with the variables. It says it has ones on the diagonal. Basically, we'll say from top left to bottom right. On the left side of the vertical line. And now you could easily just as say that you could, if you didn't have it here in the augmented matrix form, you could also have it back here where you would have like 1x, you'd have 1y, and you'd have 1z on this thing. And everything else is going to be zeros when it comes off that. And all the other values, we'll say on the left-hand side. So all the other values on that left-hand side are going to be 0. The camera just zoomed out on me all of a sudden. Not sure why. I'm not sure when it backed out on me there. Okay, and what that's going to look like, just kind of give you an idea here. It would basically be something like that. And the whole point of reduced row echelon form is that if you get to this one, then if you can have a matrix rewritten so that it looks something like this, it makes it really simple, because this would basically be this is your z variable that you have. So you've got that z would equal 4. This would tell you that you've got y is equal to 3 and x would equal to 2. So if they ask you, for something like this, your solution would just be 2, 3, 4. So if you can get something, and what they try to show you is that, all right, if you take a matrix that you have and you can get it down to the point where you've got this one variable equal to here, you can kind of work the equation backwards so that you can eliminate all these numbers back here so that you can get it to the point where you've got a solution that's written here, which is great, but there's a lot of extra work that you have to do to make it look like this, and you can get the answers to me a lot easier way um, than having to do that. So what we're going to do is we're going to try to focus on it so that we get it down to the point where we have some values like this, but we're also going to have other values in here that, this could be I think this pencil broke earlier. You can also have an 8 in here, or you can have a 2 or a -4. So we're not going to worry so much about having the reduced row echelon form where we have just ones and everything else is zeros, which is great. We're just going to focus on it so that we've got kind of this diagonal type thing. We've got other numbers here, which will be okay. Because we can put it in reduced row echelon form, but it's just a lot more work than what we have to really do to get the answers for what we're looking for. Okay, now one other little thing with reduced row echelon form that's here. If the last row is all zeros, then your last variable value is just the variable. So if we had just kind of go back, put it back in real quick. I don't know if we can do this, but let's say we had one more zero set through here, and then at the last part of it, we had something like this. Okay, so if we had something like that, I'll give you an example of it here in a second where it's a little bit better. Then you basically the last, if that had been the setup here, and I'll give you a better example of it here in just a second, just kind of give you an idea. But if we had something like that put in here, we'd had X would have been the 2, 3, and 4, but then this last value would have been a W that would have been here. So if we had gone one more value where we needed one more point, if we had one more row of zeros all across the bottom, then we'd have the W value that would have been here. The thing is that when you do that, all the other values that we have for X's and Y's and Z's, those will actually be in terms of W. And let me give you an idea. Let me show you what that's going to look like when we do one of these. Because a lot of times in those, it won't exactly be, it won't be in reduced row echelon form. It'll be in something that's kind of similar to it when they go through these. So it won't be exactly like reduced row echelon form, but it'll be something fairly close to being in reduced row echelon form. Okay, so let me show you what that would look like here. Okay, so there's the problem that we'll use and kind of go from there. Okay, so here's one where, again, it's not quite reduced row echelon form. It's got ones on the diagonal, but you've got some more numbers that's up here, and this last row is all zeros. So for this one, again, this would be X, Y, Z, and W. So we don't have any values here for W. So this is basically, for this part of it, when you've got all zeros on the bottom, this is saying that this is just W. It doesn't have, we've got 0 equals 0, which is, this is where, if we had a problem like this earlier back in the last section, this is where we said we were going to have infinitely many solutions. And this one's going to kind of be that same way, that there are an endless amount of answers you can get from this one. But because of how this thing is set up, we're going to put it in terms of this last statement, because we actually, if we took away this row, this last row that was here, we've actually got values that we know that for this part of it, without this last row, we'd have that y, or this would be z would equal 5. That we could kind of go back and take this one and use it to go back and get some other values. But because of this last one here, we don't know what the w value is, so we're just going to say, all right, it's just some number, because you can plug in any number here that you want to. But by doing that, all these other values are going to kind of spin off this one that's here. Okay. All right, so for this one, we do know that z if we actually wrote this equation out, we'd have z equals 5. That's supposed to be a negative 5. I'm sorry. I was looking at that. I was like, wait a minute, that's not right. Okay, so if you had, I left that off there for a second, so go back and make that one a negative 5. So if we were solving this one, we would have that z would equal negative 5. That part we have. The other values back up here, though, they have these other numbers that's in here. So by having these other numbers, we can't just say then, if these were all zeros, then we could say that y would be negative 3 and then x would be 12. But because of these other numbers that we have in here, basically is that if we took this equation and wrote it out over here, this would be y plus 2w equals negative 3. And then what we're going to do with this equation is we're going to solve this for y. Okay, so then we'll just move that 2w over. We'll just subtract it from both sides. So then we know what y would equal. Y would equal negative 2w minus 3. All right, and then we would do the same thing for the x value that's here, because that's going to be x plus w equals 12. So basically we're taking these equations we have here and we're basically just rewriting them in a non-augmented matrix form. We're just writing them out in equations. And then for this one, we're going to solve for x. Well, if we solve for x, we're just going to subtract the w. I'll put that over here. That's w, negative w plus 12. Or you could do 12 minus w either way. And then from there, you're just going to write out the answer. So x is negative w plus 12. Y is negative 2w minus 3. Z, we actually got a number. It was negative 5. So that one was okay. And then again, this last part, because it was all zeros, we're just going to say that that's w. So this will be the answer that you're looking for here. In x, y, z, and then w form. Okay, so if the last row is all zeros, then your answers are going to be in terms of w when you go back and solve this. Now, again, you may have one like this where it had just the one value for z that was here, and that's okay because of how it was set up. Because if you notice on this equation, nothing back here has z in it. These are all zeros, so this is okay that it's got just a number here for that value of it. Okay, and then they use this example to kind of walk back into the next part of this one, that they talk about 3 different types of solutions. And it's the same thing we were looking at back in section 1, but they just they give it some different names here. That if you have one answer, you have one solution, kind of like we had back here for this one, that if we had a solution for this augmented matrix, it was 2, 3, 4. If you get an actual answer without any variable values in it, then they say that that's going to be an independent solution or an independent system. Okay, if you have an answer like this one, where that if you get to the end of it and we've got one equation where you've got like 0 equals 0 and there's an infinite amount of answers you can do here, then instead of calling it infinite solutions, kind of like this one was, they're going to say, all right, instead of calling it that, we're going to call it dependent. I always kind of like doing this one because if you get a problem like this, then you're going to have, sorry about that. To me, it's one of those things that if a problem like this, if you've got 0 equals 0, to me, that's kind of like a does statement. So I always see that as being like dependent. And if you want to kind of tie some things together and how that goes. So if you get an answer, a question here that's got a does statement in it, if you get like 0 equals 0, to me, that's where you know that that's going to be dependent because, well, there's a million different answers that can work on this thing. So anyway, so that's one way I always kind of tie those two things together. So if you've got a does statement, it's dependent when you look at this problem. And then the last thing you have, last time we were looking at two parallel lines that didn't have a solution. Well, instead of it being no solution, which is, I mean, really what it is, they get a new name. They say this thing is inconsistent. I'm not sure why they always have to add something to it and change the names, but in this case, this is where, you know, it kind of pops up like this. So now how that would look for something that's inconsistent is that for a problem like that one, you would have basically down here, you would have all zeros on one side, and then you have your vertical line here, and then you have like an 8 or a 4 or any non-zero number. Because in that case, you know, you've got 0x plus 0y plus, you know, 0z equals 8. Well, how can you have 0 equal 8? Which doesn't make any sense, right? And that's the same thing we had before back in section 1. Now they just kind of got it written a different way when it comes off of these. So that's kind of your three things you're looking at. You got one where you have just like actual solutions, and that's going to be you get one answer that's got, you know, a certain value for x, a certain value for y, and a certain value for z. That's independent. If you have a problem where you've got the infinite solutions where you've got, and it has to be basically on the augmented matrix part of it, you'll have a 0 equals 0 statement in there somewhere on one of these rows. That's dependent. And then if one of the rows would have, you know, if we were doing the same problem and you had like 0 equals, you know, 18 here at the end on that one would be no solution because there's no way that 0 could equal 18. So that would be part where you have something that would be no solution. Okay, so there's your three options of what solutions you may have when you do these. Okay, now we haven't really done anything yet because we've talked about it and done everything with it. So here's what we're going to, now we're actually going to solve these. And again, there's all kinds of different ways you can do this. They talk about Gauss-Jordan method. You've got the elimination method. You can do the augmented matrix method. You got all these things for all this stuff that you can do, but really it all still comes down to the same thing. Okay, if you're solving a 3x3 system, the best thing that you can do, and you can do this all kinds of different ways when you go through these, but normally you want the first row, and this is one you don't have to do this, but it does kind of help a little bit if you can make it this way. But it doesn't. The book will tell you that you've got to make the first row or make the first equation so that the leading term is 1, which is great, but you don't have to do that. To me, this is kind of an easier way to look at it with how you set this thing up. So this is kind of my rules for it. So this is not exactly what's in the book, but to me, this is what works for me to make it so that you can do the least amount of work and still get the correct answers, and it still be mathematically sound when you go through these. So here we go. So here's my rules when I go through this one. You want to eliminate the same variable two different times using two different pairs of equations. Or in this case, they're calling them rows more than they call it equations on these. I like to call them equations because it's equation 1, equation 2, equation 3. Whether you call it equations or rows, it's still basically the same thing here. Okay, now when you're doing this one, what I would key on this part of it is I would say when you get to a problem like this, you want to key in on the variable that basically has, if you can find one, that has an x value or a y value or a z value, because that's usually what we're going to have is just x, y, z with the 3x3 systems. The easiest one to do this is to use a variable that has 1 as a coefficient. Now, and sometimes when you do this, you may only have one variable that's got 1 as a coefficient. Sometimes you may do this and you may have it so that all 3 variables may have 1 as a coefficient. If that's the case, then you've got all kinds of options you can do on these. Okay, so if you can eliminate the same variable 2 different times using 2 different equations, well, now you've gone from a 3x3 system, now you've got a 2x2 system. So then you can just basically go back and solve. You're going to take those 2 new equations that you have. So we're going to take the 2 new equations that we've made from the 2 different, eliminating the 2 different variables, or the same variable 2 different times. And we're going to take those 2 new equations and solve like we did in 6.1. And by doing that, you don't have to learn a new method. You basically take the same thing we were doing in 6.1, and now you're just going to take it and just redo it a couple of times to kind of go back and do this. You don't have to learn a whole new system. You don't have to worry about, getting it in reduced row echelon form where that you've got ones on the diagonal. Okay, that all looks really neat, but if you're just trying to get an answer that you've got, you're going to get the answer the same way, but you're just not going to have to do near as much work as if they talk about putting it, just flashing back here, in reduced row echelon form. Because, yeah, this is great because you got an answer that's 2, 3, 4. All right. But it's a lot of work to get it to look like this, that we're not going to worry about making it look like that, because you can get the answer doing a lot less work the same way every single time and come up with this one. So whether they tell you to solve it with the Gauss-Jordan or the augmented matrix or whatever other method they tell you to use in here, it all still comes back to the exact same way of being able to solve these problems and doing the same thing. So you can solve them all these different ways and still get the same answer, and that's what we're going to do here. So, all right, so let's give you some examples of what this thing's going to look like. Okay, so we'll start with x plus 3y minus 6z is equal to 7. Make sure I don't miss any signs when I write these down. We've got 2x minus y plus 2z equal to 0. And then x plus y plus 2z equals -1. And this is one of those that you have to be careful because with the 3x3 systems, if you get one sign off, and I always have to be careful and write these down, because if you're off by one sign, it can throw the problem off, and you go from having nice looking answers, and all of a sudden you've got really odd, weird answers that are just bad fractions to work with. Okay, so to stick with the method they're talking about, basically we're going to call this row 1, row 2, and row 3. If we were in Math 112, I would call this equation 1, equation 2, and equation 3 just because of the way the book is set up, but we're going to stick to the same thing that's here. Okay, now if you're going with what the book would say, the book would say that you have to start with it so that you want the top number to be a 1, which is what we have, and then we're going to eliminate x from this part, and then we'll get it down so we've got these two things that's here, and then we're going to eliminate the y's so that we get it down so that we've got something like this. So we'd have a 1 here, we'd have a 1 here, and we'd have a 1 here, which is great, but you don't necessarily have to do it this way. Because with this one, you could eliminate z using these two equations and eliminate z using these two equations to go with that one. You could definitely do the x's here because you've got x that's here and x that's here. You've also got a 1 and 1 here. You could also eliminate the y's here. So there's really all kinds of different options you can go for this one. So for this one, just to be, if you want to, just so it kind of follows what the book does, but again, we'll kind of break off and show you something different from where the book would go different. We're going to eliminate, actually, I'm going to change that one. I'm going to eliminate the y's in this case because I've already got a negative y here and a positive y here. So the very first thing I'm going to do is I'm going to add row 2 and row 3 together. Because if I do that one, I don't have to do anything at all to eliminate this y variable that's here. All right, now when you do that, don't forget that you do have 1s with all these variables. So if you have a variable that's by itself, and that's something I've seen people will forget sometimes. They'll get in such a big hurry to solve everything else. You'll forget about this 1 that's here. So go back and put a 1 on that x because this is 2x plus 1x for 3x. 2z and 2z is 4z equals negative 1. Okay, so in this case, and you may want to see what we did here, we eliminated y. All right, we're going to do the same thing again. We're going to eliminate y again, but now we have to use a different set of problems, or different set of rows for these. So we cannot use row 2 and row 3, which means we're going to have to use row 1, and you can either do row 1 and row 2, or you can do row 1 and row 3. So we just can't use the same two. We're going to have to use, row 1 and either one of these two. Since this is already negative, let's do row 1. And then we're going to take row 2 and multiply it by 3 and add that together. Okay, so here's where we eliminate the y the first time. Here's where we're going to eliminate y again. So we're going to take row 1 and we're going to do 3 times row 2 to make that 6x minus 3y plus 6z equals still 0. Okay, and again, don't forget there's a 1 there. So we've got 1x plus 6x for 7x. That goes to 0y, and that's what we wanted. It's out. Now, in this case, we got a bonus because when we put these two together, that goes to 0z, which means that's also out. So we got kind of a bonus on this one that we got 7x is equal to 7. And if we had done this like we were going to do, normally we would have had another z that would have been here. And if that would have been the case, we would have brought these two equations together. This had been, 1z or something in here. We would have brought these two equations together that we've kind of made now. And then we would solve this system just like we did back in section 1. We would eliminate the x, or we eliminate the z, and we'd go from there. The bonus is on this one is that when we did this one, it's already got it solved here because we've got 7x equals 7. Well, we don't even have to do anything for that one. It's already solved for us. That means that x is going to equal 1. So that one came out kind of nice because it already kind of worked its way out, and we got an answer without really having to do much of anything, that it just kind of worked itself out here. Once you got it down now, we just go back and do back substitution. We'll take this value that we have here, and we're going to plug x equals 1 and plug it back into this equation that we've got right here to figure out what z is going to be. We're going to take this value and plug it in for x right here. That's 3 plus 4z equals 1. Subtract 3 from both sides. Oh, that's a negative 1. Forgot my sign there. Hang on. Okay. That's 4z equals negative 4. Divide those two numbers, so we've got z is equal to negative 1. Okay, and then just like we were doing back in section 1, once you've got one of these answers, you can go back to any of the original problems that you have and plug it back in to find the other variable. In this case, we're going to do the same thing. You can take these two values that we have now for x and z, go back to any of these original problems and plug in x and z and then solve for y. To me, the one that would be the easiest one to plug into would be row 3 because it's already got the y by itself. So we're going to take x equals 1 and z equals negative 1, and we're going to plug that into that equation. Okay, now again, which one you pick to plug it into, it doesn't matter. I'm just going with the one that looks like it would be the easiest. So that's 1 plus y plus 2 times negative 1 equals negative 1. So that's 1 plus y minus 2 equals negative 1. We've got 1 minus 2, so that's negative 1. Add 1 to both sides, so we get y is equal to 0. Okay, so final answer in ordered triple, because we've got 3 different values here, would be 1, 0, negative 1. And that's an x, y, z order. Okay. All right, before we do another, any thoughts or any questions or comments? All right, let's give you another one of these. All right, I know sometimes y'all don't like it when you have fraction answers, so let me give you a problem that works out where we got a fraction answer, just in case that happens to work out. I think most of the answers will be whole numbers, but you may get an occasional one that's got some fractions, so let me just give you one just to make sure. Okay, so here's the system we'll use for number 2. Okay, now if we stick with the way the book does it, we'll do this one on this problem because we already have like an x and a negative x. So this one to me would be easy to work with. Now, same thing with the y's. You've already got a negative 1y here, so this would be easy to work with. Same thing with this one. You got a negative 1z. So this is one of those that you could solve any equation you wanted to, any way you wanted to, because no matter what you do, there's always an easy way to get rid of either the x or the y or the z because they all have a coefficient of 1. You got a 1 here and here. You've got a 1 on the y. You've also got a 1 on the z. And whether it's negative or positive, it doesn't really matter. But as long as you've got a 1 that's on one of the variables, that's what we're going to do. But we're going to kind of stick with the way the book does because we've got the x's, so this will be easy to work with. Now, one of the things that the book will tell you is if you stick with what they want you to do, is that if you're going to do it in reduced row echelon form or all those, it's easier if this first value of x is 1. So they would tell you to actually rearrange this thing and rewrite it. So we're going to basically just swap row 1 and row 3 when it comes down to this one. And this would be where they would tell you to interchange row 1 and row 3. Okay, and anytime you're working with these, just make sure that you're careful about your signs, because again, if you get one sign off, it can throw the problem off in a hurry when you go through these. All right, so here's what I would do next if this were me, because we've got to eliminate, if we're going to eliminate x in this case. So to me, the very first way to do this one, to eliminate x, is we're going to eliminate x. And the one that's kind of jumping out at me when we're doing this is that I'm going to go ahead and do row 1 and row 3 because those are already positive and negative, so we're just going to add those two together. Negative x plus 3y plus 2z equals 0. Easy there, the x's are out and gone, so now you have 5y plus 5z equal to 0. Okay, then we're going to eliminate x again. And again, if we stick with what the book would tell you, that you want to leave this part x here, so now we're going to take negative 2 times row 1, and we're going to add that to row 2. Because if we make this a negative 2 and make that a positive 2, then we'll put those together, that'll make that x go to 0. Okay, so that would be negative 2x minus 4y minus 6z equal to 0. And then 2x minus y minus z equals 3. Okay, x's are gone, which is what we wanted. Now you have negative 5y minus 7z equals 3. Okay. Now, and here's where I kind of break off from what the book would say, because the book would say, if you've got it here, so now we've got this new system that we've made, and I'm going to put this on a scrap sheet of paper here. They would tell you that, okay, now that you're here, you're going to have this new equation that we have, that we're going to have, we've got x plus 2y plus 3z equal to 0. They would tell you, all right, well, now what we're going to do is we're going to take one of these two equations that we have, and we're going to solve it just for y. So, and to me, that would be this case, you would, or to get so that y is equal to, has a coefficient of 1. This would be the easiest one because now you've got so that you can divide everything by 5. So we would take this equation and just basically say, all right, that's going to be y plus z equal to 0. And then they would take, now here's the part where I would agree with them. They tell you then to take these two equations that you have that's here, and we're going to pull these two equations together. And you're going to solve these two equations. You're going to eliminate the y variable, and now you're going to solve for z. Okay, that's okay. But to me, this is where we're going to take these 2x2 systems here. Instead of adding another step to what we're going to do, now you just solve this one, and you solve for either variable that you think is the easiest one, whether that's y or z. It doesn't matter. In this case, it just happens that, and it would be really easy to solve for y here because it's already 5 minus 5. So we can just add these two things together. The y's will cancel. We get negative 2z equals 3. Well, then we would solve by dividing by negative 2. So that means that we have z would equal negative 3 over 2. Okay, and then the book would say, oh, now that you've got it here, now you've got z is equal to negative 3 over 2. Well, then they would tell you, all right, well, now you take this equation that you have, and you're going to eliminate the z variable from this one. So then we're going to take this equation and we're going to multiply it by negative 1, and then we're going to add row 2. We're going to do negative 1 times row 3, and we're going to put that together, and now we've got a new equation that's here, and we're going to solve it for y. But when you do that, it adds more steps to it. So for me, it's like, okay, once you get it down to here, we've taken this 2x2 system and we've solved it. Now we're just going to go back and do back substitution. We're going to take this variable that we've got here, and we've got this value for it, go back to either one of these two equations and plug it back in and tell me what z is going to be. So now we're doing it just like we did in section 6.1. So once you get it down to a 2x2 system, forget everything else. Just solve this 2x2 system. You've got the one value here. Plug it back in. Let's see what the y value is going to be. I don't think either one of them, I mean, because you've got to, there's not any way this is going to cancel. So to me, there's not really an easy one. I'm just going to go with the 5y plus 5z equal to 0. We're just going to plug that back in here and solve it. And there's not going to be any way around this one. It's going to be in fractions because we've got negative 15 over 2 equals 0. So here, now you're going to solve for y. You've got 5y would equal, we'll add the 15 over 2 over here. If you're one of those people that you don't like fractions and you get here, remember, you can just go back and multiply both sides by 2. And this will eliminate that fraction. So then you get 10y equals 15. And then we can divide by 10. So y would equal 3 over 2. And now that we've got z is equal to 3 over 2, y is equal to 3 over 2, we can take those two values. Now we can go back to any of these original problems that we had back up here and plug in these two values for y and z that we have. Okay, I ran out of room, so I'm going to put this over on the side over here. This will be our last step. We've got that z is equal to negative 3 over 2. Y is equal to 3 over 2. And we're going to plug that into any of the equations. There's not, they're all going to have fractions in them no matter what we do. I'm just going to go with the last equation. But again, it doesn't matter. You just pick one equation that you have and just start plugging it in to see what you can come up with. All right, so x is by itself. We got 2 times 3 over 2. Okay, that's good. The 2's cancel. And then 3 times negative 3 over 2 equal to 0. Okay, so that one, those cancel, so that's x plus 3. That does not cancel. That's going to be negative 9 over 2 equal to 0. If we get a common denominator, that's going to make that 6 over 2. 6 minus 9, that's going to be minus. It's going to be minus 3 over 2 equal to 0. So then we add the 3 over 2 to both sides. So that is 3 over 2 for x. Okay, so final answer then is x is going to be 3 over 2. Y is also 3 over 2. And then z was negative 3 over 2. Okay, so when they talk about solving elimination method, I agree with them most of the time, but once you get it down to here where you have just you've eliminated the same variable twice. Now again, they tell you have to do X. You don't have to do X. You can eliminate X or Y or Z. It doesn't matter, but basically as long as you eliminate the same variable twice, take those two new equations where you've eliminated the same variable twice, pull those two together and solve that 2x2 system. That way, it's not so strict that you have to do it this way. No, you pick the one that's easiest one to you. A lot of times they'll set the problems up so that it is X. Sometimes they set the problems up so it's not necessarily X. Sometimes they set it up where that maybe Y or Z is easier to solve. But if you stick with what the book will tell you, they tell you eliminate X first, and then you can kind of spin off and go from there. But you don't have to do it that way. I mean, it's great if you do, but you don't have to. Okay. All right. So is everybody okay there, or do you think you need one more? Because I've got one more equation we can go through that's one more 3x3 systems. Or if you're good, we can go ahead and move on to section 3. Okay. So if nobody says anything, I'm going to say that hopefully y'all are okay with those, and then we'll go ahead and go on to section 3. And section 3 is applications of systems, which is basically just word problems. So the good news is you're not going to have a whole lot of problems in section 3. You're going to have, I think there's 4 or 5 word problems that you have to kind of go through and go through these. The bad news is it's word problems, so you've got to kind of dig through the problems and figure out exactly what it is that they're asking for when you go through these. Okay. So for section 3, here we go. I'm going to let it stop the video, but it seems like it takes too long for it to upload. So we'll just go ahead and put all this together. Okay, so 6.3 is application of systems. Basically, this is word problems. And the word problems, I was able to condense these down to cut out the fluff to get it to where it's a little bit easier. So hopefully you don't have to do a whole lot of writing on these. So basically there were 3, to me, I saw there was like 3 types of problems. When you're going through these, really, I almost could break it down to 2, but I saw 3 different types of problems that you have here. So here we go. Here's example 1. Okay, so we've got a moving company business type thing. We're going to say that vans cost $25,000. Small trucks are $30,000, and large trucks are $40,000. All right, so the company needs twice as many vans as small trucks. And they want to spend $15 million. But only buy 175 vehicles. And then the question is, how many of each do they buy? Okay, so there's our first word problem. Vans are 25,000, small trucks are 30,000, large trucks are 40,000. We're going to buy 175 vehicles. We're going to spend 15 million, and we need twice as many vans as we do small trucks. Okay, so very first thing is we've got to figure out, there's our variables that we've got vans, you're going to call them X, small trucks are Y, and large trucks are Z, because we've got to have some combination of these. So this is where you take all the word problem that's here and you figure out what your three equations are that you're looking at. Okay, so they're buying 175 vehicles. So the first thing I see is that we've got X plus Y plus Z equals 175. They're going to spend 15 million, so that is, here's where the numbers get a little bit long. $25,000 for every van. We're going to spend $30,000 on the small trucks and $40,000 on the big trucks, and that's going to come out to be 15 million. Okay, and the last one, which really probably been the first thing we wrote down, the company needs twice as many vans as small trucks. So, ever how many small trucks we have, we're going to double that number to get, X is equal to 2 times Y. Because we're going to double the amount of small trucks to then get the amount of vans we have. Yeah, so we need X is equal to 2Y. Okay, so there's our system. Now, the one thing we want to do with this one, actually with this equation that we have here, this is what we need, but we want to set it up so like a system so we have for this part. So we're actually going to take this equation that we have that's here and take this one and rewrite it as like X minus 2Y equals 0. So if we set this system up, we've got X plus Y plus Z equals 175. I'm going to go ahead and put this one next. So we're going to take that one and rewrite it so it's there. And then the big one at the end, and that's the one that's no fun to work with because the numbers are just so large on that. So that's the system that we're going to work with to solve this thing. Okay, so we're going to do the same thing that we did in the last part. Is we're going to work with this one to eliminate the same variable twice. And then we go from there. Now, here's what I would say on this one. Because this one already has Z that's missing, I would say let's take this one. So we've already got Z that's eliminated. So if we've got row 1, row 2, and row 3, I would say since Z is eliminated in row 2, let's just eliminate Z using row 1 and row 3. Because even in a problem like this one, if they've already eliminated one, if one equation has one of the variables that's missing, they've already done half of that elimination process we were talking about. That if you're going to eliminate the same variable twice, well, they've already eliminated Z for you here. So now we can just take these two equations and eliminate Z again. Okay, so to do that, we're going to have to take negative 40,000 times row 1 because we need that to be positive and negative. So we're going to take row 1 times negative 40,000 and we're going to add that to row 3, which is not going to be very pretty, but anyway, we'll get it going here. Okay, so that's going to be negative 40,000 X, negative 40,000 Y, negative 40,000 Z equals, let's see if I wrote that out here. went through the setup here. I did not do 40,000 times 175. So let's see what that's going to be. That is 7 million. So that's a negative 7 million. Trying to write that small because those numbers were long in here. Okay, and then we're just going to bring in the original row 3. Okay, the good news is when we do that, we're going to have a little bit more room because the z's will be gone. So we've got negative 15,000 x, negative 10,000 y equals 8 million. Okay, so we eliminated z, and again, we already had z eliminated with row 2, so now we're going to take this small equation we've got here, this now big equation we've got here, and we're going to use these two equations to eliminate either x or y. It doesn't really matter when we get down to that one. Okay, so let me take that to the next sheet of paper here. Okay, so now we're going to have x minus 2y equals 0, and then this big equation here. Good news is that's a 0 at the end, so that'll make that a little bit easier. Okay, so they had already, when we set this thing up, we already had z going out of this one, so we took the other two equations to eliminate z, and now we're here, and now you pick whether you want to get rid of z or you want to get, you want to get rid of x or you want to get rid of y. The numbers would be just a little bit smaller if we'll take the top equation that's here and multiply it by 5,000. Let's see, that one's negative, so we need to multiply by negative 5,000 because this is already negative 10,000. We got to make this a positive 10,000. Now, if you're one of those people and you're bad about your signs, this might be where you would want to, instead of multiplying by negative 5,000, maybe you want to just multiply by 15,000, which would be okay. Because if you multiply by 15,000, this will be 15,000. That's already negative 15,000. That would go to 0 right off the bat. So, if you're one of those people and you don't like changing signs, that, sometimes you're bad about forgetting the negatives, then maybe in this case you want to multiply by 15,000. And that way now we've got 15,000x minus 30,000 y equals 0. And this will be negative 15,000x minus 10,000 y equals 8 million. Okay, so that's the good news on this one is you're in control. You get to pick which one you want to do. If you don't like changing this to a negative and making that, if you're bad about forgetting some negatives along the way, then just multiply by 15,000 and cancel these. So whether you eliminate x or y, it's totally up to you. It's whichever one you want to go with here. Okay, so we've eliminated the x. We've got negative 40,000 y equals 8 million. So then we're going to take the 8 million and divide it by our numbers that we have here. And somewhere in there I missed a sign because that should not be a negative. Let me go back and double check what we did here. Well, that's terrible. Working through this problem and then we missed one. Let's see where I missed a sign. So we're on the way because we cannot have a negative amount here. So let's see. Multiply by negative 40,000. Okay. I see what I did. Okay, sorry. Back here in the beginning, I missed way back here. So this would be, that was 5 million, not 15 million. I had, when I did my dollar sign, um, I picked up that one there and thought that was, so it's supposed to be 5 million. My bad. Okay, that'll make things a lot easier. The good news is that's a simple little fix, whether you got a pen or a pencil. We'll go back and fix that here. So the only problem we've got number wise would be here. This would be a negative 2 million. Okay, so there's where we got to be careful. There's where, so that's a negative 2 million. This was negative 2 million. That's a negative 2 million. Okay. So the original problem should have been 5 million, not 15 million. That was a typo on my part. That's why they tell you just to put one slash through the dollar sign so that you don't make that mistake that I just did. And people told me that before, but I always never just pay attention to it. So, but there's one where it slapped me right square in the face. Okay, so now we're going to take the negative 2 million that we have and divide it by the negative 40,000. Okay, so we've got 2 million. Dividing that by 40,000. All right, divide those out, so that gets us at y equal to 50. Okay, so now we get to go back to any of the equations and start plugging this thing back in. To me, really easy right here. We've got the x minus 2y is equal to 0. So that one, that's screaming to plug that thing back in. So let's plug this into x minus 2y equal to 0. So that's x minus 2 times 50 equals 0. So that's x minus 100 equals 0. So that gives us x equals 100. Okay, and then to me, I'm going to stay away from that one because it's huge, and I'm going to do that. We're just going to go to x plus y plus z equals 175. So we've got y is 50. X is 100. Whoops, goes right there. We're trying to find out what z is. So that's 150 plus z equals 175. So z would equal 25. Okay, so we said this was vans, this was small trucks, and this was large trucks. Okay. So the numbers may get a little big on some of these, and some of these they'll set it up that way where you just got to kind of dig around and play through the numbers, and there's just unfortunately no easy way around it because the numbers are just going to be kind of big with it. Okay, and again, I apologize for that one little typo that we had back there. But I misread my problem when I was pulling it across there. So it's 5 million, not 15 million. Okay. Okay. All right, let me give you another one, a little different problem, a little different setup than what that one was. And then I've got one more after that, and that will kind of get us through what I saw was all the different types of problems. Everything else will just be some kind of variation of one of these problems that you're looking at. So. All right, so I'm going to do it this way so I don't mess it up here. We've got a $70,000 mutual fund. Bonds, and a fast food franchise investment, or $70,000 to invest. Sorry. in mutual funds. So it's worded a little better. So we've got $70,000 to invest in mutual funds, bonds, and a fast food franchise. You may say, well, that can't be possible. I think Steak and Shake, you can, I think for a $50,000 investment, you can own a Steak and Shake. So I can remember reading that one time. Okay, so there's her $70,000 to invest in mutual funds, bonds, and a fast food franchise. She puts twice as much in bonds as mutual funds. From what she can tell in the past, mutual funds pay 2% dividend. Bonds 6%, and the fast food franchise 10%. She would like dividend income of $4,800. And then the question would be, how much does she put into each one? Okay, and that's usually pretty much the same question that I ask on all these, is that, you've got X, Y, and Z, and we'll look at one more that's got a W in it here in a second. And, how much do we put into each one of these amounts of investments? Okay, so your setup is again kind of along the same way. That if I'm going to read through this one, I'm kind of reading this one. We'll go with the mutual fund is X, the bonds will be Y, and the fast foods will be Z. And again, the order you pick it doesn't matter. Just whatever you define it as, just make sure you kind of have that in mind when you go through these. She has $70,000 to invest, so we've got X plus Y plus Z would equal $70,000. She's putting twice as much in bonds as mutual funds, so that's just like the last problem we had where we're doing the twice as much here. So whatever mutual funds is, which is X, if we do 2 times X, that would equal Y. And now for your percentages, and this is the part that would be a little different for those. The 2%, that's 0.02X. For the mutual funds, the bonds is 0.06Y. And the fast food, basically 0.10, or you can really just do 0.1. We'll go ahead and 0.10 here. All that together is going to give her $4,800. Okay, so the 3 investments together are $70,000. We're going to double the amount that's in mutual funds as she has in the bonds. And then 2%, 6%, and then 10% for those. Okay, and so remember when you're doing those percentages, you just have to move the decimal 2 places to the left. So if you have 2%, that's going to be 0.02. So that's where we're getting these numbers from. That whatever percentage is, you move the decimal, wherever this decimal would be at the end, move it over 2 places, and that's going to be the values that we have there. Okay, now, first thing I'm going to do, if this is me, is if you don't like these decimals that's here, and most people don't, is I would take this problem and just go back and multiply this last row by 100 so you can make them all whole numbers. That might make the numbers a little bigger than what they would say to do. But if you don't like the decimals, just if you've got basically every how many decimal places you have, if you just multiply by a number with that many zeros in it, that will cancel everything out. So we're going to have x plus y plus z equals 70,000. Again, we're going to move this one around so that we've got it, so that we've got 2x. Again, we'll bring the y over so it equals 0. So we'll do 2x minus y equal to 0. And multiplying everything by 100 here, we'll get 2x plus 6y plus 10z equals 4800. And add 2 more zeros. It'll be 480,000. Okay, now this is where the problem is very similar to the last one. They've eliminated z because they talked about that, this was double this amount that was here. So I'm going to say that they've already eliminated z here, so we're going to eliminate z with equations 1 and 3. So let's do negative 10 times row 1 and add that to row 3. So we'll have negative 10x minus 10y minus 10z equals negative 700,000. And that's 480,000. Okay, and really the main reason for this one was just to go back and show you one that if you've got the percentages, just remember to move those over to the left. Everything after that is pretty much the same as was in that first equation, our first example we were working with. The z's are eliminated, so now we have negative 8x minus 4y equals negative 220,000. And then now we'll pull that together with this 2x minus y equals 0. Okay, and I would say since this is, now you can multiply by negative 4 here, but since this is negative 8 and 2, let's just take this equation and then multiply it by 4. So then this will make this positive 8x, that'll be negative 8x, and then that way we don't have to change any signs. So that'll be negative 8x minus 4y equals negative 220,000. Multiply by 4. That is negative 8y equals negative 220,000. Okay, so then dividing those two numbers, 220,000. That comes out that y is 27,500. Really short equation here. So let's plug that into here. So 2x minus 27,500 equals 0. So 2x equals 27,500. Keep putting extra zeros on there for some reason. Divide those two numbers, should be what, 13,750? Double check my numbers. Yeah. And then we'll go back to any of the original problems that have x, y, and z to get the z value. So let's just go with x plus y plus z equals 70,000. So basically, we're just going to add these two together and subtract it from 70,000. So if we do that, should be 28,750 for Z. Okay, and again, what we set this up was X was mutual funds. The Y was bonds. And this was your fast food. Okay, and then one more. And this is the one that is a, it's more like a 4x4 system or a 3x